Okay, we're going to solve this problem. I think this is the last problem on your homework assignment, and just in case you had any questions about it. Okay, so a car is parked on a cliff overlooking the ocean on an incline that makes an angle of 16 degrees below the horizontal. Okay, so that basically means here's horizontal, here's below horizontal, so it's 16 degrees, so this is your cliff. Right, it looks like that. The negligent driver leaves the car neutral and the emergency brakes are defective. The car rolls from rest, so if the car is up here somewhere, okay, and it starts at rest, and it's going to roll down the incline with constant acceleration of 2.59 meters per second squared until it for 60 meters, so it's going to go 60 meters this way, okay, during which time it's accelerating at 2.59 meters per second squared. I have a better picture in a second. I just kind of scribbling this for ideas, okay, which is 20 meters above the ocean. Okay, so then once this person leaves that cliff, okay, then they're a projectile. Okay, so then we want to know the car's position relative to the base of the cliff, so we want to know how far out before they hit the ground and probably explode. So we want to know this delta x, and we want to find the time for them to be flying through the air. Okay, so let's go over here. I have already drawn this picture a little bit cleaner. Okay, and what we want to do here is we want to remember, we want to kind of go back to last chapter. Everything from position, I don't know if you want to call this 1 or 0 or whatever, everything from this position to this position when the car leaves, it's just a one-dimensional motion problem. Okay, all of these quantities, okay, all of these are in the same direction. Okay, they're like down this cliff. Okay, so because of that, we can solve this exactly like, last chapter. Okay, so last chapter, we would have, we've got the initial velocity is 0. We've got the delta, I won't call this delta x because it's on an angle, so I'll call it delta r is 60 meters. I know the acceleration in the r direction is 2.59 meters per second squared, and I don't know the final velocity, right? And I assume that that's what I want. And to clarify why that's what I want, okay, so we'll go down here. And once this car leaves that cliff, okay, once it leaves that cliff, it's going to have an initial velocity, right? So that initial velocity might be, well, I don't think blue is the right color here, or whatever color, white. Okay, so once it leaves, it's going to have an initial velocity right here. Okay, at that point, that initial velocity, whatever that is, okay, it's this number right here. Okay, it's on an angle, and we can use that angle to get an initial velocity in the x and an initial velocity in the y. Okay, and from that we can determine what we want to do, right? But we can't do our projectile motion stuff until I know what this velocity is right here. Okay, I need to know what my initial velocity is for the projectile. Okay, so let's go up here and let's solve this little bit right here. And let's see if we can't figure out what the velocity is when the car leaves the cliff. Okay, so this has no time in it. So if there is no time, then what we always want to do is we always want to do a v squared equals v naught squared plus 2a delta r in this case. So there's acceleration in the r direction. All of these are in the r direction. So let's put some little r's on here so I remember what direction we're going in here. Okay, and the r just means it's on a diagonal of some sort. Okay, so that means v sub r equals the square root, positive or negative, I think in this case we're going to be positive, v naught r squared plus 2a sub r delta r. Okay, so v sub r equals positive or negative. Let's see, v naught r is 0 squared plus 2, the acceleration is 2.59 meters per second squared, and the delta r is 60 meters. Okay, so put a square root over all of that. V sub r equals, so I'm getting 17.6295, so we'll call that 630 meters per second. Okay, noting that we're going to have 3 sig figs in the final answers here, so so we're going to call this a positive because it's going, if I've just decided that r is downhill. Okay, so 17.630 meters per second. Okay, so I'm not worried about sig figs in this answer yet, right? We don't round early. Okay, cool. So that is my velocity right here. v sub r, the velocity on that, as the car leaves for the cliff. Okay, so we could put in, this is no longer an unknown, 17.630. Okay, so now at that point, okay, we're working forward, right? Now I've got a projectile motion problem, and I know the initial velocity on the angle. We know the angle is 17.630 meters per second. Okay, so I can zoom in and I get these two sides. So this is going to be 17.630 meters per second. Okay, this is my angle, 16 degrees. So this will be cosine 16 degrees. This will be 17.630 meters per second times the sine of 16 degrees. Okay, so that will give me my V naught in the X and V naught in the Y, right? This is V naught in the X, and this is V naught in the Y. Okay, so this is for the projectile motion portion of the equation, right? So for that, I'm going to create a little chart over here. So we'll do X and we'll do Y. Okay, acceleration in the X is always 0. Acceleration in the Y is always negative 9.81 meters per second squared. Okay, and now we've got our initial thing. So at t equals 0, t naught, I know x naught and y naught. Okay, you can do whatever you want here. A lot of people would choose this point right here to be 0, 0. That's going to keep everything positive if you do that. And I kind of recommend you do that. That's not what I'm going to do here, because I'm going to make a quote unquote bad choice, just because it's, I'm going to make this point right here 0, 0. Okay, because some of you guys might do that, right? So let's see what happens if we do that. Okay, so if x naught is 0, y naught is 0. Okay, and v naught in the x and v naught in the y. Okay, so we go over here. Here's my v naught in the x. Here's my v naught in the y. So I'm just going to plug those numbers in over here. Okay, so here's what my calculator tells me. It tells me that these are the values that we get. I want to be very careful because the v naught and the y is negative. So that's kind of an important thing to remember. And it sounds like I need to go teach some of you guys. The bell just rang. So this is, one of the things we're looking for in this problem is the final time. And we want to know the final position, right? That's one of the things we want to know. We know the final y, right? Because if this is 0 in the y, then where it lands down here is 30 below that, right? 20 below that? What was it, 20? I didn't label this cliff. Okay, let's see here. The cliff, which is 20 meters high. Okay, so this is 20 meters. 20.0 meters. Okay, so let's zoom in. So that means if this point is 0 in the y, this point right here is a y coordinate of negative 20. Negative 20 meters. Okay, and we'll note that the v and the y, when the velocity of this thing in the vertical when it hits the ground is unknown, so we'll just leave that empty. And the v and the x, the velocity when it hits the ground, remember we always know this because the acceleration in the x is 0, so we always have the same velocity at all times in the x direction. Okay, so now we are set up with this information. We should be able to solve this problem. Note that before I go to class, it is, this x is easy once we have time. So it's a lot of times easier to do time first. And that's probably the way I'll solve it. I guess we'll see what happens when I come back from class. All right, see you. All right, so I'm back from class, sitting on my couch, thinking about this problem. And what I want to note here is that, so we're going to do a problem and we're going to be looking for time for this thing to fall. So, here's everything that we have. Okay, and the key here is time. Okay, now the hard thing about this problem, and I want to, it's never not worthwhile to say we've got a delta y, okay, which is going to be negative 20. I've got an initial v naught, and I've got an acceleration. So what having all three of those things mean is if I want to use this equation, delta x equals, I'm going to do this in red because I guess it'll show that I'm not doing this, at squared. Okay, there's a y right there, there's a y right here. I guess I put a delta x, and I should have a delta y. So let's put a little y in there. Okay, so for this equation, if I've got a delta y, which I do, I've got a v naught in the y, and I've got an a in the y, then this is going to lead to a quadratic formula. Okay, so this is going to lead to t equals, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Which means, yes, I can solve it. I can solve for time using this equation. However, that is usually not the way that we're going to go, because that is just a little bit harder. Okay, so instead what I'm going to do is, using the values in here, I'm going to solve for Vy first. Okay, this is all just to avoid doing this. Okay, so to solve for Vy, if I don't have time, remember this equation is going to be Vy squared equals V naught in the y squared plus 2a delta y. Okay, this is an intermediate step. We don't actually care about Vy. I don't think we care about Vy. I don't have a question mark here, so I'm assuming we don't actually care about the Vy. Anyway, so we'll go ahead and solve this. So Vy equals positive or negative square root of V naught y squared plus 2ay delta y. Okay, so Vy equals positive and negative. Let's plug in some numbers. V naught in the y is 0 squared. That's nice. Plus 2. Oh, sorry, that is the wrong number. Let me erase that. V naught in the y, right? So that's this value right here. So that's going to be negative 4.6711 meters per second. That's going to square, so that negative doesn't really matter. Plus 2 times ay, negative 9.81 meters per second squared, times the delta y, which is negative 20 meters. Okay, I don't think I need to tell you this, but that is where the error is going to show up, is forgetting to put that negative right there on the 20, or forgetting to put it here, right? Anyway, so if we solve this particular, I almost call this like a side problem because it's an intermediate step, okay, so I'm going to get 352 meters per second. Okay, and I'm going to note in this case it's a positive or negative, so I'm going to take the negative because it's going downwards in the y direction. Okay, this is an intermediate step, so I'm not going to bother taking 2 sig figs or 3 sig figs. I'm not going to worry about sig figs for this particular problem. All right, so good. Okay, now what are we solving for? It's been so long. It's been all a long day, and I don't remember what we're solving for here. What are we looking for here? Let's see, where are our question marks? Question marks, I want to know how far from the base it's going to land, and I want to know time. Okay, so once I got Vy, then time comes out of this particular equation. Vy equals V naught y plus 2a, sorry, not 2a, at, right? Ay times t. Okay, so if I rearrange that, I'll say t equals v in the y minus v naught in the y divided by ay. Okay, be very careful with your signs here. So t equals Vy, which is negative 20.352 meters per second, minus v naught in the y, which is this number right here, negative 4.6711 meters per second. Again, just be very careful of those negative signs. And ay is negative 9.81 meters per second squared. Okay, so t equals 1.5985 seconds. Okay, again, intermediate steps, so I'm not worried about sig figs. I'm just going to keep too many. Okay, so we got our time. Oh, I guess it's not an intermediate step, right? So that is one of the answers that we wanted. So maybe I'll write this in blue. We want to know time equals 1.60 seconds, 3 sig figs. Okay, boom. There's one of our 2 answers. How long is it in the air? Not very long, but I mean, if you think about it, it's only falling 20 meters, so it wasn't a huge cliff. Okay, the last question. Oh, we want x. So we essentially want delta x, right? Because we started x naught at 0. So delta x and x are the same thing. But we'll go ahead and use the full quote-unquote displacement equation. So, always remember x direction is really nice and pretty because it's a simple thing, especially if you already have time, and we do, right? So the first thing to be aware of here is that this term is going to go away because a in the x is 0. Okay, so the delta x equals the v naught in the x direction, which presumably we got. We did. It's 16.290. It's this one right here. Okay, 16.290 meters per second. And how long were we moving in that x direction? 1.5985. 1.5985 seconds. Okay, so delta x is whatever those numbers are. Is 26.040 meters. Okay, so the delta x equals 26.0 meters. Okay, that's 3 sig figs. Now, if you thought, well, maybe we really just want x, well, that would be fine. You could do, well, x minus x naught equals 26.0 meters. The x naught is 0, so x is 26.0 meters. Okay, either way you wanted to write this, I would accept. Okay, so there you go. That's it. It's going to take 1.60 seconds, and it's going to land 26 meters out. All right, so hopefully that's helpful, and that's it, 16 minutes. All right, see you guys. Take care of yourselves. Bye.